okay, to recap this, the for a game to be fair, okay, the expected returns of the game has to be 0. Okay, as you can see here. Can you see this?
Yeah.
Yeah, the expected gain. Okay, this phrasing expected gain, right? Okay, is very vague, because sometimes, okay, let me illustrate. Let me illustrate this. Okay, for certain questions, right? At least for this textbook, right? How they define the equation is as such: expected gain is equals to expected returns minus the cost of playing. Okay. Yeah. So this is how this book define the equation of fair games. Okay, but for some textbooks, right, or rather in some questions, so you got to be very flexible. They define these expected returns as expected gain. They take the returns as gain. Okay, so this one and this one, there will be a conflict. In terms of just the name, but the whole logic is still the same. Basically, if you want to look at it in economics term, right? Okay. Oops. Okay, hold on. If you want to look at it in economics term, right? It will be the expected profit will be equals to expected revenue minus the cost of playing. Yeah.
Yeah, okay. This one.
Yeah, I think you can relate to this more because you're an economics student, right? Yeah. So we can just take it as this: expected profit equals to expected revenue minus cost of playing. Basically, whatever that is here is what you are getting back with and not less the cost yet. This expected gain and profit over here is what you get after you less the cost. Okay? Can okay. Let's try a question first before we okay, let's try question 10 first on your side. Let me screenshot this.
Oh, I did it. Wait, have I done this? Oh yeah, I did already.
I send you, is it?
Yeah.
Is it that I send you? Can you send me so we can go through together?
Yeah. Hey, wait, I rewrite this again because it's a bit messy.
Sure.
Okay, wait, I'll send. Do you think we can go to binomial distribution today?
Confirm. 100%.
Okay.
100%.
Because I am again confused.
No problem.
Because like if we use GDC, right, my teacher says like this type of binomial distribution, then we can use like the GDC for like PDF and CDF.
Yes. Yes. You're right. Okay. Let's review the question. A person plays a game with a pair of coins, means he has two, right?
Hmm.
He has 2 coins. If 2 heads appear, okay, so he's going to get H and H. Then he will win $10. If a head and tail, okay, or it could be a tail and head, right?
Hmm.
And then $3. If 2 tails, maybe tail and tail, then $5 is lost. Okay, so this one plus 10 plus 3 minus 5. Okay, how much would a person expect to win playing this game once? How much? Okay, they're asking for how much. Means we are looking at the what?
Expected
The expected what? Okay, sorry. Let me write this out. Expected profit is equals to expected revenue minus cost. So is it asking for the profit, revenue, or what? Is it asking for the expected profit or expected revenue? Minus cost yet or not?
no. Yeah, minus with what?
Sorry again. This $10 here, $10, $3, minus $5.
Haven't cost yet, right?
Okay, so in this case, right, this one haven't factored in the cost yet. But the funny thing about this game is that, okay, is that if you lose, you need to pay money on top of the cost. We haven't talked about the cost yet. We haven't talked about the cost yet. But the different thing about this question is that if you lose, it's part of the rule that you have to pay the $5. Yeah. So what will happen at the fun fair is that, okay, you go to this store, so you have to pay to play. Okay, you have to pay to play. So we don't know how much is that cost first. Okay, let's say we already pay $2 for instance. Then after that, you are going to like flip 2 coins. If the 2 coins is tails, then you're going to pay $5. You know, you're going to lose $5 on top of the $2 that you pay to enter this game. Get what I mean? Okay. So over here, what the question wants us to calculate is this. Okay, the expected revenue. Because we do not know the cost yet. This cost here is still a question mark. Because the question did not mention what is the cost. So therefore, 100% in part A, we want to find the expected revenue. Okay? Can. So usually, how we want to go about doing a fair game question, right? We always want to draw the DRV. We want to draw the PDF. What is PDF? The probability
distribution function.
Yes, probability distribution function. Okay, so we know that what we want to find here is how much. So our random variable now should be x equals to amount of money won. Because after that, we are going to find how much a person expects to win. We are trying to find the expectation of the amount of money won. Therefore, we have to define our x as amount of money won first. Okay? I mean, this is the more favorable way of presenting. It's not that your way is incorrect. No. I mean, there's one mountain, but there are many ways to climb it. So, but I will always prefer you guys to present it in terms of a table, because this is what you guys learn also. I mean, a tree diagram, you guys learn in a tree diagram also. Yes, I agree. But in the form of table, we will see things much clearer. So we have so x is the amount of money won. So it can either be -5, 3, or positive 3 or 10, right? So over here, it will be x, probability of x equals to x. Then now we have -5, we have 3, and we have 10. Okay, so from here we want to find what's the probability of getting -$5. So you have calculated here using your tree diagram. Very good. Okay, so to get -5 means we get tails and tails, which is 1/4, right? Okay, to get heads and heads will be is half times half again is 1/4 again, right? So by right, do we still need to go and calculate heads and tails? We don't need. Why?
Because you can just 1 minus.
Exactly. 2, which is 2/4, isn't it?
Yeah.
2/4 is also 1/2. So everything you presented here was correct. Okay. Yeah, just that in a table form, it is very slick. It is very clean, very concise. Yeah. So from here, we want to find the expected amount that we win. Okay, the expected amount we win. So from here is very clear cut already. All we need to do is to multiply this, multiply this, multiply this, and then we add them up, right? Just need to add and add. Then we will get the answer, which is over here. So we expect to win like maybe $2 ish, right? From here. Always put it in terms of the, you want to add the units. So it's like $2 and what? 75 cents?
Yeah.
Right? Because it's 2 3/4, so it's $2.75. Correct? Okay, nice. So part B. If the organizer of the game wishes to make an average of $1 per game, okay, how much should the organizer charge people per game to play? So let the fees be K. Net profit will be K dollars minus, okay. Okay. Yes. Yes. Hold on. Oh, wait a minute. Net profit equals to K minus. Okay, let's take a look at this equation. Expected profit is equals to expected revenue minus cost. Okay, this is from a player's standpoint. Correct? This is from a player standpoint. Okay. So now as the organizer, the player's profit is our what? Our loss, right?
Player's profit, yeah, loss.
Yeah, player's profit is our loss. So the player's revenue, okay, so over here, the player is expected to make like $2.75. So now you let the fees be K. Yes, it's correct. Okay. So we want the player. Oh, wait a minute. Wishes to make an average of $1 per game. We have to net profit equals to K dollars minus the fees be K dollars. Actually true. I think this way will be too confusing. I think your way is more feasible. K dollars minus K dollars is the fee charge.
Yeah.
How much should the organizer charge? We want to make an average. So now we want the organizer to make $1. If the organizer want to make $1, so the expected revenue could be, so if we had the chart back, right, it would be minus 10, minus 3, and 5. So this will be 1/4, 1/4, and 1/2 again. So it would have been, let me calculate. 0.25 times minus 10 plus 0.5 times minus 3 plus 0.25 times 5. Minus 10, minus 3, and 5. So the expected... why do I get... Yeah, so I will get minus 2.75 minus k. So these are in the standpoint of organizer, the expected revenue will be the negative. So also the cost would be... Yeah, you're right. Actually, yeah, you are right. Okay, I know how to explain to you already. Oops. Okay, I know how to explain to you. Your method is correct. Okay, but I want to use this equation because this is the equation. This is as in the concept of fair game revolves around this equation. Yeah, so I want to use this equation to explain to you. This one is like using common sense lah, right? It really makes sense to calculate it this way. Okay, but using the equation to explain, it will be this. Okay, from an organizer's standpoint, the player's profit is organizer's loss. Yeah. So over here, the cost, yes, we will leave it as K dollars, which is in this case, if you want to calculate, the... Actually, like that, I think I might confuse you. But never mind, okay, never mind. I think I shouldn't go through this. We will just take it as, we will just use your method to solve it. It's okay.
Okay.
Can? Yeah. Oh, shit, I still feel like explaining to you. Okay, let me explain. But if you don't get it right, you just stick to your way of doing. Can?
Okay.
Okay, so organizer standpoint. Okay, so our expected profit... Oh my god. Is equals to player's loss is equals to our expected revenue will be our fees charged minus our cost of playing, which will be players' revenue. Make sense to you?
Yep.
Yeah. Okay. Our expected profit is the player's loss, and our expected revenue will be the fees that we charge, because that's what we get without deducting the cost of the playing the game. And the cost of the cost borne on our side is basically what the players can stand to win. Right? Okay. So right over here, I want our expected profit, because the question says we want to make $1 per game. So this here will be $1. Right? The fees charge will be K dollars. The player's cost, okay, the cost will be $2.75. So with that said, from here, you want to solve for K, it will just be 3.75 plus 1.
2.75 plus 1.
Sorry, 2.75 plus 1, sorry. Yeah. And therefore you get your answer here. Yeah. I mean, this way of expressing, no problem. Okay. It's just that I just want to explain using the fair game equation.
Yep.
Okay. Was there another question?
Question 14.
Okay, you can send me first.
Okay, let's see. Again. Haven't yet. Did you get it?
Just.
Okay.
Okay. All right. At a charity event, there is a money raising game involving a pair of ordinary die. Means it's a fair die, yeah? Okay. The game costs $8 to play. Okay, now we know. Cost of playing $8. When two dice are rolled, their sum, okay, so X is the equals to sum of the score. Okay, maybe instead of this, right? I should do this now. Cost of playing is $8. X is equals to the sum of the scores of two dice. The organizers decide that a sum which is less than 4 or between 7 and 9 inclusive is a loss of this. Okay. So right now,
What happened to the ABC the question?
that's what I received.
Wait. I sent both.
Oh, sorry. It's at the top. Okay. Okay, let's minimize this first. Let's put it at the corner. Okay, so we know that if less than 4 or if X less than 4 or X between 7 and 9 inclusive, okay, it will incur a loss of will be minus A divided by 3. Right? Okay. So the organizers, a result between 4 and 6 will give you plus 7. Okay, I think so I write easier. Okay, if X is between 4 and 6, it will give you plus 7. A result of 10 and more will give you, wow, $27, man.
27?
21 bucks, sorry. So determine X lesser than 3. So X lesser than 3 will be what?
Will be
S
3
equals to 3.
like 3 I put 1/12, but it's like if you slowly write everything, if you write everything up, right, it's 3/36. That's why you get 1/12.
Okay, so this is when you have to show, you cannot just jump straight to the answer. So how do we present it, right? Is this. So x lesser equals to 3 means we want x equals to, sorry, we will want the first die, which is x1, okay, be equals to 1, and x2 be equals to 2. Right? Because if we sum it up, we will get 3. Then the next one would have, sorry. We talk about getting 3 first. Getting 3 first. Then the next one will be plus probability of x1 equals to 2 and x1 equals to 1. Sorry, x2 equals to 1. So that's all for getting 3, right? And then the next one will be getting 2. How do we get 2? It will be 1 and 1. Right? No other ways, because in a die we cannot get 0, right? Yeah. So over here we will be getting 1/6 times 1/6 to the power of times 3, which you will get your 1/12. So this is what the marker will want to see, this portion here. Okay? Okay. So for 4/6, okay, for 4, from between 4 to 6 would be, to get 4, it will be probability of x1 equals to 3 and x2 equals to 1. Okay, so the other way around will work too. So over here I need just times 2 plus probability of x1 equals to 2 and x2 equals to 2. No other ways really. Yeah. To get 5, it will be probability of x1 equals to 3. Equals to 4 also can. Okay, we use the way. 4 and x2 equals to 1 times 2 equals to 3 and x2 equals to 2 times 2. Yes. Any other ways?
Nope.
No more, right? Then to get 6, x1 equals to 4. Sorry, 5. And x2 equals to 1 times 2. This one also times 2. We have x1 equals to 4 and x2 equals to 2. And the last one will be
3.
Yes. Okay. So what we have here is 1/36 times 2 plus 1/36. 1/36 times 2, which is 2/36. 2/36 again. 2/36 again. 2/36 again. 1/36. So we have 1, 3, 5, 1, 3, 5, 7, 9, 10, 12. So it's 12/36. So this is correct and this is correct. Okay, so I will not, this is, what I'm trying to show here, your answers are correct. What I'm trying to show here is just to show you the mode of presentation only. Okay, I'm not going to do again. This is very boring already. Okay, next. Okay, part B. Show that the expected gain of a player is given by this. Okay, so over here, they're asking for X.
Wait, you need to show it in the exact form, like in the question.
What do you mean?
Because you see my answer is the same thing, but I forgot to put the 1/6 outside.
Put the 1/6 outside.
Like the answer is correct, but then I put divided by 6 instead of time.
Actually it's fine. Actually it's fine, but
I think better to
yes.
Okay,
better to
yeah.
do that.
Mm.
Yeah. So in this case, because they already gave you the cost of playing.
Yep.
So since they gave you the cost of playing, so the expected gain they are talking about here will be to minus the cost. Okay. Yeah. Because according to the textbook, just now, if you remember, right, where in the notes of this textbook, right, their expected gain, they are talking about the expected profit.
Yeah.
Yeah, but now, sorry. This is also still expected profit. Yeah, it's right. But I have seen in some other textbooks, right, the expected gain, right, is basically their expected revenue. So sometimes it can be a bit confusing that way. Okay, next. What would the value of A need to be? Okay, anyway, this is correct. What would the value of A need to be for the game to be fair? Okay, so you just have to equate to 0. But the presentation, again, the presentation is very important. It will be very good if you can write out, like for game to be fair, expectation of, or rather expected gain, you can just write out expected gain should be equals to 0. Then from here, then you can carry on with this. Okay? Explain why the organizers will not let A be equals to 4. Okay, then let's take a look at the next picture. Okay, because if A is 4, organizers will make a loss. Yes, precisely. Very good. And no one wants to go into a loss one. Okay, part 5. If the organizers let A be equals to 6 and the game was played 2,406 times, estimate the amount of money raised by this game. Yeah, correct. Very good. So, you see, you want to make money, right? You just got to make sure, right, that it's not a fair game. Yeah. So if you can create a game that's not a fair game and people pay money to play it, there you go. That's why casinos waste money. It's true. Then it's like it's auto run some more, and you don't have to market for people to come and gamble. Naturally, people just want to gamble. Okay, now it's binomial distribution. Okay, for binomial distribution, okay, we have not touched on this yet, right? And today we are going to this new topic. Okay, firstly, let's go back to the whiteboard first. What's the whole, have I explained to you the concept of binomial distribution? Like, in binomial distribution, what are we distributing? What do you think we are distributing? It says binomial distribution. Like, what are we distributing here? Okay, this topic is under what?
Prop.
Under statistics, right?
Oh, yeah.
There's another statistics. In statistics, we deal with this one thing called what? Starts with P.
Probability.
Yes, probability. And this is what we are distributing, probability. Remember back then in discrete random variables, we have this what? PDF, right? Probability distribution function. Okay, where we learn about the probability that each and every value can get. Right? So from the probability distribution function, we know of how the probability is being distributed between the between all values of the random variable. Make sense? Okay, but back then when we distribute this, this was like an anyhow distribution. Okay, there was no sequence for how we distribute it. Okay, but right now we are learning the binomial distribution. Okay, the closest that we ever got to binomial, right? Back then in probably year 4 or year 3, right, was binomial theorem.
Oh.
Right? Okay. Or also the binomial expansion. Do you remember this? Yeah, we also learned like just a few months back on binomial theorem. Remember this thing, the TR plus 1 equals to N choose R A
N minus.
Yes, BR, right? Yeah, we learned about this. So but where did this binomial theorem or expansion come about? Okay, it came from this thing called Pascal triangle. Okay, it came from this thing called Pascal triangle. So what is Pascal triangle? I'm not sure if you still remember what your teacher taught you back then. Okay, Pascal triangle looks something like that. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay, how all these values are being created is via these means. Okay, so we see that 1 and 1 will give you 2. Okay, 2 and 1 will give you 3. 1 and 3 give you 4. 3 and 3 give you 6. Okay, so if you were to take a closer look, why is it called binomial distribution? And we are distributing probability. We see that across the whole sequence, right? Okay, across this sequence of numbers, right? We see that the numbers ascend to a peak. Yes, then it descends. So it's going to go up, then it comes down. Right? There will be a peak right here. And for binomial distribution, this is what is going to happen also. So we are the probability when we say that this random variable is binomially distributed, it means that the smaller values and the larger values will have like the lower probability. Somewhere in the center, right, will have a higher probability. Okay, so in other words, to put things into perspective, it should look something like that. Let's say the number of goals a soccer player score. So maybe this is 1/8. Maybe this is also this is 2/8. This is 3/8. This is 1/8. How many already? 1/8. Yeah. So we can see that the probability goes up, then it comes down. Right? So we can say that, okay, I mean, this is just an example, although these two are equal. Okay, just an example. So we can say that this will be a binomial distribution. So this is how it is going to look like. Can? Okay, so this is just the overall concept of binomial distribution. Okay, so in binomial distribution, right, there are a few features. Okay, so in binomial distribution, for it to be a binomial distribution, it must respect these four requirements. Okay, F, I, S, T. Okay, so what does F represent? Okay, F represents that there must be a fixed number of trials. Okay, what does trials actually mean? Trials basically just means, right, the number of times it happened. The total number of times it can happen. Okay, so let's say in a soccer match, okay, let's say Sean in your school, ACS International. Okay, we want to know, okay, he played in 10 soccer games. Okay, or rather, sorry, he took 10 shots. Okay, he took 10 shots. I mean, like, when I mean shots, I mean like a soccer shot. It's not like a liquor shot. Okay. Okay, so he took 10 shots. Out of these 10 shots, right, okay, the probability of him scoring a shot is like maybe 60%. Okay. Okay, so say Sean took 10 shots. Okay, the probability of one shot scored is equals to 0.6. Okay, so 10 will be the fixed number of trials. Okay, we are not going to calculate anything more than 10 because we are just going to base the probability based on these 10 shots. Okay, so out of 10 shots, we want to, using binomial distribution, we will be able to understand, oh, what's the probability of him scoring, like, let's say 4 shots. We'll be able to calculate just by using the parameters. Okay, but okay, coming back to this. So firstly, you need to fulfill this requirement, which is it must have a fixed number of trials. In this case, is 10. Okay, I is independent. Okay, every single event must be independent. In this case, what is the event that is independent? Okay, the shots. Every single shot he take, right, is independent of each other. Okay, basically we have to take in the assumption that he doesn't feel sad that he missed the last shot. He will still take this shot as if like it's the first shot that he's going to take. So that every single shot that he takes, right, it is independent of each other. We have to assume it that way, because these are all assumptions and facts of binomial distribution. So what is S? S means same probability. Okay. The probability of him scoring a shot should always be the same. I mean, since they are independent of each other already, the probability has got to be the same, right? Makes sense? Yeah. So lastly, it will be 2 outcomes. It's a very bad color. Okay, lastly, it will be 2 outcomes. So what are the 2 outcomes? It can either be a success or a failure. Okay, so means it's either he score a shot or he doesn't score the shot. There cannot be like another outcome, like it must either be that he win or he lose. There cannot be draw. There cannot be 3 outcomes for it to be a binomial distribution. Like when you go to school, it's either you are late or you are punctual. Okay, you cannot add in the probability of you being early, because early means punctual already. Understand? Okay. Sorry, this is I hope this, I mean, this is bound to be a bit dry because I'm talking about content first. Now we can go to some questions. Did your school give you any binomial tutorial that you want to ask me first?
Wait.
If yes, then we can do it together instead of doing the questions here, so it'll be more efficient.
I mean, the question that I have is more on CDF instead of PDF.
Sure. So why not you send me first?
Yeah.
Just send me whichever, everything. We can just go through everything, no problem.
Maybe I find the. Is the thing. Okay, wait, I'll take a picture, then I send.
Sure. Give me a minute, I go to the restroom first.
Okay.
Back.
Okay. Do you see the question?
Yes. Okay, let's keep this by the side first. Okay, let's take a look at this. If even or Ivan, Evan likes to play 2 games of, what's that? 2 games of chance. Oh my god, sorry. This thing is very, let me bring it down. Okay. Evan likes to play 2 games of chance, A and B. Okay. For game A, the probability that Evan wins is 0.9. He plays the game 7 times. Okay. Before we even do anything, let's break down this question first. Okay. So there are 2 games that he wants to play. Okay. So now we're talking about game A first. Okay. For game A, the probability that he wins is 0.9. Okay. So in binomial distribution, there are 2 very, very, very important parameters that we need to include. Okay. Is N and P. What is N? N is the number of trials. P is the
Success, right?
probability of success. You're right. So something very important that I want all of you people to know is that the probability of success, right, is affected, okay, or determined by how you define the X. Okay, but how you define the X? What is X? X is the random variable. Okay, very important. Okay, so from here, then we can go and proceed to solve this question. What are the steps to solve a binomial distribution question? Step number 1. Define the random variable X. Okay, so in this case, we'll be like, let X be equals to the number of times Evan wins game A. Okay. Step 2. Define the distribution. Oops. Okay. Then step 3, we are going to define the problem. Okay, how do we define the distribution? So the distribution will be X follows, the curly arrow means follows, and capital B means binomial distribution with parameters, in this case, 7, 0.9. Okay, it cannot be 0.9, 7. Okay, it must always be in this format. N, P. Okay, then the third step is define the problem. So it means exactly 4 games. So X is equals to 4. So this is binom what? PDF. Okay, because it is an equal sign. Okay, so when do we use binom CDF? Okay, when it's an inequality, yes, but there's a very, very specific kind of inequality. It must be lesser,
like more than or equal to.
It must be this.
Oh.
There cannot be any other kinds when you use binom CDF.
Oh.
Yeah, you must change it to this.
Okay.
Okay, so what happens if, let's say, for instance, if I have X greater than 3. So X greater than 3, if you draw the number line, okay, for me, I will always draw the number line if I cannot see it. So I know that I have 1, 2, 3, 4, 5. Greater than 3 means what? Okay, means from here onwards.
No, but it's greater than 3 means doesn't include 3, what?
Correct. That's why I use a hollow circle.
Oh, yeah.
Yeah. So how can we translate this to give us this inequality over here? Okay, we have to use 1 minus probability of x lesser or equals to 3.
Oh, so is this the
Complementary.
Is this like the Q, like 1 minus the probability of? No, it's not.
No. I'm just saying that if right now I want to find the probability that Evan wins more than 3 games.
Oh.
If I want to find the probability of Evan winning more than 3 games, and we want to use the calculator, right? Use the calculator to calculate binomial CDF. We have to convert it into x lesser or equals to 3. This is the turning point.
Oh.
Understand? So let's say, for instance, if I have px greater or equals to 3, so it will be 1 minus probability of x lesser or equals to 2. Make sense? Because px greater or equals to 3 means now this will be a solid. Yeah, so I have to minus this side onwards. So some students will ask, hey, Kenny, then what about the portion over here? Okay, remember, this is binomial distribution. For binomial distribution, we only are looking at integer values. Okay? Yes. So I hope you understand how to do, so these are the templates. This is the step to do it. Okay, so for part B, write down an expression in terms of B. Sorry. Okay, for game B, Evan wins P. And the probability he wins is P. Okay, he also plays 7 times. Write down an expression in terms of P, the probability that he wins exactly 4 games. Okay, so which means, right, this is the non-calculator question. Right? And you should know the formula for you should know the formula for binomial distribution, which is probability of x equals to x will be equals to
n choose
it's in your formula booklet. You don't have to memorize that. You have a formula booklet.
Not with me now.
Okay. It's basically just n choose r.
Oh, okay. Then
it is the binomial. It is the TR plus 1 term that you memorize.
Oh, okay. Then a to the power of.
Okay, you use p because in this case it's the probability of success.
P to the power of n minus r. Then yeah.
Okay. Yeah. So it's just like that. Okay. So over right now we want the probability of, because now this number here is no longer 7, and now it is, oh sorry, it's still 7. It's just that it's the other way around. This is p. So we want x to be equals to 4. So, sorry, this is r. So it be equals to
7 choose 4.
So p is just p. 4. Sorry. 7 minus 4. 1 minus p.
Power 4.
Yeah. So this will be the expression. Then I say hence, find the values of p. Values, they say values. So obviously there's more than 1, right? That the probability that he wins exactly 4 games is 0.15. So right now we can substitute value in. So 0.15 is equals to 7 choose 4, p to the power of 3, 1 minus p to the power of 4. So over here, is this a GDC question or non-GDC question?
This question, they don't really say. I
Yeah.
think we because we could use the calculator for finding the PDF and stuff.
Yeah, so I think in this question they want, it's a hands question. So it's usually, oh sorry, this is definitely going to be because usually statistics is in paper 2. Yeah, so definitely you can use the GDC, but over here we cannot use the GDC to straight away find this. Okay, because they want us to use this equation. Okay, we have to plot the graph into your GDC. Then we sketch another horizontal line of 0.15. Then we find the intersection. Understand what I'm trying to say?
Yeah.
Yeah, so that's how you solve this question. Any questions?
Yeah. Oh, okay. So you just graph it lah, and then you find the. Wait, but what are you finding in the graph? Like.
Okay, because you have this. Okay, alternatively, right, you can bring the 0.15 over to the other side. So you have your 7 choose 4 p to the power of 3, 1 minus p to the power of 4 minus 0.15 equals 0. So from here, you just need to find the roots.
Oh, okay. Okay.
Better, right?
Yep.
Can I move on?
Yep.
Okay. The probability of obtaining heads of a buy, okay, it's a buyer's coin, so you cannot say it's 0.5, it's 0.18. Okay, the coin is tossed 7 times. Okay, up to this very point, we can identify that, oh, this is telling me that this is the probability of what? Success, right?
Probability. Oh, so the like in the NP thing, this one is P lah.
Yes, means this is the probability of success. So if this is the probability of success, can you tell me what is the X already? If you want to define the random variable. Because step one was to define the X, right? So you have to let X be something, right? Yeah. So if P is the probability of obtaining heads, the probability of success is determined by the definition, remember? Just now I mentioned. Remember, right? Hello?
Yeah.
I repeat. The probability of success that correlates to the definition of the random variable. Okay, so since we know the probability of obtaining heads is 0.18, so it means this is the probability of success, which means the probability of, the definition, the step 1, when you need to define X is equals to the number of heads obtained. That's right. Okay, so step 2, we have to define the distribution. So X follows binomial distribution. Number of trials? 7. Probability of success?
0.18.
Yes. Step 3, define a problem. So now we look at 7a. Obtaining exactly 2 heads. So probability of X equals to 2. Simple, right?
Oh.
Yes.
So this is PDF lah.
Yes, this PDF, you're right. Binomial PDF. So for part B, we want the probability of obtaining at least 2 hits. So it's x greater or
Equal to
2. So, but the thing is, look here. Right now, this is a problem to us. Px greater or equals to, we want to use CDF, but it cannot allow that. We have to manipulate it, right? Manipulate to what?
you have to wait. The complement thing, right?
Yes, which is what?
So is
Take your time to think.
So that means you have to change to x is smaller than or equal to smaller than or equal to.
If you cannot see it, draw the number line. Number line will always work. What we want is here onwards.
Doesn't mean you're looking for like 1 minus the probability of it being less than of the probability of x being smaller than or equal to like smaller equal to
Smaller equal to what? You're still confused? If you're still confused, look here. This is the probability that we want. This whole portion. So to get this portion, we are going to use 1, which is the whole probability. Okay, 1 is the whole probability. Minus away
probability of x
this portion.
or equal to.
Sorry again?
Is it not smaller than or equal to 2?
No. How can you do that? You're including 2 here already. You minus away 2, then how can you include 2 here? You think about it. You want 2 to be inside the x. How can you minus away 2? How can you minus away this?
Oh, so it's 1.
Yeah, it has to be 1. Make sense to you? We try another one. X greater or equals, okay, probability of x greater than 5. Think. How do we do the manipulation? We'll do it a few times until you totally get it.
So this one is 1 minus probability of x being lesser than 4.
Yes. 1 minus probability of x lesser or equals to 4. You're right. Okay, we try another one.
This one is 1 minus probability of x smaller than or equal to 3.
Yes, you finally got it.
Wait, then if I do things like that, then it's without calculator lah. But if it's with calculator, cause my GDC right, no need to do this.
Oh wait, your GDC can use upper bound and lower bound for your.
Yeah.
Oh, then in this case you don't even need to don't even need to understand this really.
Yeah, so does that mean if we just use the CDF thing for part B, right? So does that mean you put the binomial CDF is 7, then 0.18, then 2 and 7, because the
2 and
is
7, yes.
Oh, okay.
Yeah.
Oh, okay. Can.
Yeah, like that you don't even need to know this.
Okay.
Well, this is like so much easier.
Oh.
Okay.
What's question 8?
Okay, question 8. Okay. A factory makes calculators. Over a period of 2%, over a long period, 2% of them are found to be faulty. Okay, so what is it trying to tell us here?
That your does it mean your your number of trials is 100?
No, wait. I haven't even reached there. I'm here.
Or so probability of, can you say probability of success is probability of it being like okay, like not faulty?
Why would you want to do that? Because of the word success, right?
Yeah.
Okay, so this is something this is something that we need to take note in binomial distribution. Success. I mean, in this world, right? Success has a very positive connotation tied to it. Okay, but the thing is, you can successfully be late. You can successfully be faulty. You can successfully be bad. You can successfully be an evil person. That is still a probability of success, right? So how we want to define a probability of success has to be according to the context of the question. So in this case, what is the probability of success in this case? It's the probability of the calculator being faulty, yes. So the P, which is probability of success, will be 0.02. Understand? Then over here, they say sample of 100 calculators. So you will write your N will be equals to 100. So step number 1, what is step number 1?
Determine
The what?
The X follow B.
No.
Huh?
What's step number 1 I mentioned just now?
You
define what?
Define what is the random.
Yes, the X. So X is equals to what?
Number of faulty calculators.
Correct. Because how do you know? It is from the probability of success here. This is how they define it. So next, step 2 will be defining the what's that called?
PDF, right?
No. The distribution.
Oh.
Defining, yes, in a sense, yes, but we always say define the distribution. So it will be X follows binomial distribution.
100.
100.
Then 0.02.
Yes. Okay. So next one. AA. Find the number of find the expected number of calculator. Expected number means what? The expectation, right?
So it's N times P?
Yes, N times P. Very easy.
Oh.
So that's for part A. For part B, find the probability that 3 calculators are faulty means?
Your X is probability of X equals 3.
Exactly. Very easy.
Oh.
For part C.
Probability of X is more than equal. More than one. Not more than. Also more than equal to 1, yeah. Wait. More than 1, more than 1.
Okay. So this one very easy to find, right? So what's your lower bound?
What's the lower bound? 2.
2, correct. Okay, so in other words, we can also use 1 minus probability of x lesser or
Then
equals to
1 minus probability of x less than or equal to 1.
because over here we did not include 1.
Oh, okay.
Here we have to include 1. Okay?
If you were to use the
If you use
calculator,
GDC, you don't need to care about this.
then that means the upper bound for this one will be is the upper bound 100?
It has to be.
Yeah. Okay, yeah.
Can Is any more questions for binomial?
Not from this worksheet.
Okay.
Because
So
this was the last worksheet we did.
okay, previously you mentioned that you had issues with CDF. So
Yeah.
is it rectified yet? So this is what you wanted to ask, right?
Yeah.
Okay. So with that said, right, I will send you some questions on binomial CDF questions.
Okay.
Then same thing, we'll go through the next exercise.
Okay, can.
Okay, if not, then that'll be all for today.
Okay, thanks.
Okay, bye-bye.